Okay, this last test we're going to be working on this semester looks at measuring in-place density of compacted soil. And last week we looked at the Proctor compaction test. And what the Proctor does, right, is by using this mold, it tells us what the maximum achievable dry density is for a particular soil. So on any construction site, you're going to have to take soil samples of what's in place and see what its proctor is. And if it's not able to achieve the density needed for the compacted subgrade portion of your project, it has to be stripped off and hauled away, and import material has to be brought in from a gravel source. And any material, whether it's on site or brought in as a foreign material, has to have a proctor test to know what that achievable densities is. So the in-place density tests measure the density of soil after compaction. And typically contractors are required to achieve 95% of whatever the proctor result was for that material. And if you remember, the proctor test also allowed us to determine the optimum moisture content. And this is the moisture content at which the maximum dry density is most easily achieved. So this is important information for the contractor to know, because they're going to be able to attain this 95% of the proctor with less compactive effort or less time in order to get the specified result. And this is just two examples of some construction projects I just happened to be going by one day and took pictures of. On this site you can see all this dark, kind of loamy black soil has been stripped off. It's great for growing crops, but it's pretty poor when you want to use it on a construction site. So it's stripped down to a depth necessary so that the correct depth of import or strong materials can be brought in and built up to the design grade. So it looks like though they may be stripped out about 3 feet here, and at that 3-foot level you essentially have this compacted subgrade, right, of existing ground. On top of that, they're laying some sort of kind of a coarse geotextile fabric, and then it looks like a good 18, possibly even maybe 24 inches of pit run before they're starting to bring in crushed gravel, for a nice base course. But this compacted subgrade and also this sub-base material both had to have in-place density tests run on it, right? Every layer in this kind of a sandwich, essentially, if you think of it that way, has to be tested for compaction. Typically, the lower you are in this horizon, the weaker the material. So maybe your proctor results for this loamy soil might be 105, maybe 110 pounds per cubic foot. Compact or pit run could be 110, 115 pounds per cubic foot. And then when we're bringing in crushed gravel, we're going to get higher strengths. It's a little easier to see here on this road section. This is Highway 191 in Montana, and it was excavated all the way down to the compacted subgrade. And you can see these different layers. There might be, looks like, definitely 3, possibly even 4 layers here, where this is, looks like some pit run material. There might be some sub-base, some larger, maybe 2-inch minus, meaning the largest particle sizes in that layer are 2 inches in diameter, which would fit through a 2-inch sieve. Then we have base material, which is typically 1-inch minus material, 1-inch crushed gravel, maybe 1.5 inches crushed gravel. If it's really expensive and you can afford it on a job site, you might use 3/4 inch gravel. Right, the finer material, the more mechanical screening or mechanical sieving it has to undergo at the gravel pit, so it's going to cost more. And then on top of that, you have a surface course, or looks like about 4 inches of asphalt. So every one of these layers had to have in-place density measured on it before the next layer could be brought in, right, and compacted on top of it. And we have 4 different, I guess, exhibits of strength going on here, where we have this weak compacted subgrade, a slightly stronger sub-base, a little bit stronger yet base materials, and then typically your strongest course is that surface course, whether it's concrete or asphalt. So there's 3 main methods for measuring in-place density. This first is probably not a method you're ever going to see, and it's called the balloon apparatus. And we do have one of these devices in our lab. I'll show it to you, but our pressure bulb here is kind of a rotted rubber, so it's actually not effective. But how it works is you dig a small hole out of the soil that you're measuring the density on, and then you want to obviously measure the mass of the soil that you've just excavated. And in order to compute density, right, it's mass over volume. So you need to know the volume of that material that you just removed. And the way a balloon apparatus works is you stick essentially a rubber balloon inside this chamber that's sealed off down here at the base. This chamber is filled with water, and then you pump pressure into the chamber, and it forces water down into that balloon, which then expands and fills up the hole that you excavated. These gradations here are measured in cubic centimeters, and we know a cubic centimeter. Well, what we know is if we can measure the displaced water in cubic centimeters, we know that the hole that water is now occupying is that many cubic centimeters of volume. So that's a real easy way to measure mass and volume of a portion of compacted soil. More common, but still not very commonly done anymore, is a sand cone assembly. And a sand cone assembly works the same way, right? We have this kind of a template plate that we lay down on our soil that we're going to be testing. We excavate out a small portion below that plate, and then we fill in that hole with a material of known density. And what we use is Ottawa sand. It's a very uniform, very predictable sand. And if we can measure the mass or the weight of sand it took to fill up that hole, and we know the density of that sand, right? Well, density and mass can be used to calculate volume. And that's another pretty simple way of measuring the volume of a hole that was excavated out of soil. And if you know the volume and you weigh the amount of material that came out of there, you can measure it, or you can calculate its density. And this is the test that we'll be doing this week, is a sand cone assembly. The most common method now on job sites is to use a densometer, or a nuclear densometer. And it's a device that has a small amount of radioactive material on the tip of this rod here. Cesium-130 something or other. I forget the exact molecular number. But a sensor, I think a helium tube sensor in this densometer, reads a scatter of the atoms, or of the radiation coming off of that source material, and it's able to derive a density of the medium through which that scatter is occurring. The benefits of a nuclear densometer are you get instant results, right? You don't even have to wait for the time it takes to do a calculation. You don't have to wait for moisture content results to come back. It's non-destructive, right? We don't have to dig a hole like we do for sand cone or even balloon apparatus. So you're not, well, they're actually digging a hole up here in this picture, but I think that's just for kind of a random sample. You don't have to dig a hole for the nuclear densometer. And it also actually instantaneously measures moisture content along with the density, right? It's got um, a different sensor in here that measures, I guess, the effect that the hydrogen atoms in the water that occupies this soil have on that count. So it's able to um, give you a very accurate moisture content without having to wait for drying results in an oven. So we're going to be looking at the sand cone apparatus this week in this test, and it's done in 3 parts. And this is a copy of the data sheet that comes out of the lab. And we want to make sure we don't forget before we head outside to do these first 2 parts, right? This first part is determining the density of the sand that we're using before we even go outside. And typically that's done using a Proctor mold, right? We know the volume of a Proctor mold, so we're just going to fill it up flush with this Ottawa sand, and that'll allow us to compute the density of the source material, right? This sand that we're using. Part 2 then is to calibrate the cone of the sand cone assembly, and that cone is that metal device we looked at here that sits flush with the surface of the ground. And we want to know what's the weight in pounds of the sand it takes to exactly fill up just that cone. So we'll do that on the table before we head outside as well. And then part 3 is to perform the density test in the field. And the density test is just what it's shown here in the bottom, is we have this template that we lay on the ground and we excavate out a portion of the compacted soil, staying within the limits of that template. You want to go down a couple inches, about 4 inches, and you're going to retain all that soil in a container so that you can weigh its mass. We want to know what's the mass of the soil that came out of that hole. We also want to be able to compute its moisture content, so we're going to have to weigh it wet, we'll put it in the oven, and then come back and weigh it dry. So in this diagram here, the hole we dug is shown by this this cross-section view here, and that's an empty void, right, before we put the sand cone apparatus on top. We'll place the sand cone apparatus on top. It fits right into this little lip on the ring of your plate, and then we open the valve, and it's essentially just like an hourglass, like a sand hourglass, and the sand comes out of the plastic jug, goes through the hourglass, it fills up the empty void that we want to determine the volume of, and then it also fills up the cone that we know the volume of, or we know the mass of. So what we're able to do is use the displaced weight of sand that originally occupied this jug with the sand after the test, or the weight of the sand after the test. And that's represented by this kind of void space here, where this was your original sand level, and this is your new sand level. So if we know it took that much volume, or that much mass of sand to occupy our cone and our hole, we can determine the volume of our hole. The final week of the semester, we're going to just have a demonstration on densometers. This is by far the most common. This is what you'll do. I have heard that there are some companies that will still run a sand cone maybe every 100th test just to check the calibration of their nuclear densometer, because you're essentially trusting a digital readout here. I think I've heard Wyoming DOT might also require some sand cones periodically. I've heard some of the tribal contracts in Montana require sand cones periodically. But for the most part, you're going to be using densometer if you're a field inspector measuring density on a job site. So the way that's done is you're first calibrating it on a density block, a block of known density, so that your radiation is calibrated for the day. You then you pound a hole. You don't have to dig a hole, but you do have to pound kind of a pilot hole through your soil, so that this insertion rod, right, can be inserted down into the soil there. you get a more accurate reading, right, when this source rod is inserted at a 6, 8, or 10 foot depth below the ground, because you get this radiation scatter coming up through the soil to the detector. That's called a direct reading. And the direct reading on these devices give you accuracies within, less than a half of a pound per cubic foot accuracy. So it's very, very accurate and very, very quick. This also can be done in what they call a backscatter mode, where you don't pound a pilot hole and you don't insert this source rod. Just like this bottom picture shown, this rod is fully extended all the way up. And that's done on fresh asphalt or existing asphalt, where you don't want to punch a hole through a brand new black ribbon of asphalt there. You'll still get good results. You'll probably double the tolerance, the accuracy tolerance, and get results a little over plus or minus half of a pound per cubic foot, which is still typically plenty accurate for the materials that we're working with. And lately, or the last couple years, this kind of new device has been showing up, and it's still made by the same company that kind of dominates the nuclear densometers. It's a Troxler, and they market it as an E-gauge, where the source material now on this rod is a much a lower grade of radioactive material, and you don't have to have the same licensing to operate. These nuclear densometers, you have to go through a certification exam and training, not so much to operate them, but it's really about locking them down and transporting them, because they are regulated by the Nuclear Regulatory Commission, and that's why we don't have any at the school. It's just too expensive and too much of a pain to actually own one of these things. But these E-gauges are kind of changing the landscape now. You don't have to be certified or licensed to own, store, operate, or transport them. They give you essentially instantaneous results. So it's a little slower than a nuclear densometer, but not that much. And there's an electronic device here that can measure moisture content as well. So the last week of the semester, we're going to have some former students from WET, Water and Environmental Technologies. They're a consulting company here in town, and they own, I think, 2 E-gauges here. They're going to just give us a demonstration on how these work, and we can compare the E-gauge results against the sand cone results that we do in lab this week.